this chart is about reference frames and relative motion. So to begin, consider that we have two coordinate systems. Coordinate system A, drawn upper right, and then lower left, coordinate system B. And they are separated by a position vector RAB. And so this is the position vector of coordinate system A relative to B. In particular, it's the origin of each coordinate system. And let's say there's a point C, which would be described from the vantage point of coordinate A with the vector R vector CA, and it would be described from the vantage point of coordinate system B with R vector CB, and each one of these is drawn. So there is a vector relationship connecting R vector CB with R vector CA, and that is R vector CB. You can see it from the picture here. R vector CB is the sum of R vector AB plus R vector CA. And I'd like to write that in the opposite order to reinforce the thought here. If you just look at the subscripts, CB, RA, AB. So it's just as if the A's disappear and you get CB here, if you see what I mean. So if R vector CB is equal to R vector CA plus R vector AB, describes the positions in the two coordinate systems, the time derivative of everything in the first equation gives the second equation. That means that VCB is equal to VCA plus VAB. So in words, the velocity of C relative to coordinate system B is the velocity of C relative to A plus the velocity of A coordinate system B relative to A. So to show you an example of this, let's say that we had a river. Okay, so here's the river is flowing down in my picture. Let's say it has a velocity VRE. E means earth, R means river, so this is the velocity of the river relative to the earth. Let's say it's 1 meter per second down. So in arbitrary units, I'm drawing the river flow being downward. And let's say a boat embarks from the left bank, and when it is in the water, it has a velocity of the boat relative to the water straight across horizontally of 0.5 meters per second. Well, if I want to find the velocity of the boat relative to the earth, which would be appropriate, for example, for a person standing on the bank, anchored to the earth, in other words, that would be VBR plus VRE. And so VBR is the velocity of the boat relative to the water. That would be this vector here. So this is the vector sketch corresponding with this equation, plus the velocity of the river relative to the earth. And that's this downward vector. And so with this data, the boat is going to end up going at some downward angle, and its velocity, its speed relative to the earth is going to be the magnitude of the sum of these two vectors, in other words, the magnitude of this vector, and that's just, since this is a right triangle and this corresponds to the x direction and this to the negative y direction, just going to be equal to the magnitude of the first plus the magnitude of the second, each one squared, the square root of the sum of those. And so that ends up being 1.12 meters per second if you do the math. And then the angle with respect to the perpendicular to the bank, that would be this angle theta here, is simply 10 minus 1 of 1 divided by 0.5. Well, that's the inverse tangent of 2, and that ends up being 63.4 degrees. So a couple of questions for you. Let's assume, first of all, that the river is 500 meters long. None of that has been 500 meters is not important to the argument that I've made here. But if the meter is that wide, then if we assume otherwise that everything is the same, how long would it take the boat to cross the river? And how far downstream would the boat go? Okay, and question 2. Um, the question there is, let's first of all assume that the boat is going at 2 meters per second rather than the 0.5 meters per second. At what angle should the boat travel? Should the boat travel if it ends up traveling perpendicular to the riverbank? And so conceptually, you have to point the now 2 meter per second velocity of the boat relative to the river at some angle upstream relative to the perpendicular. And what angle should be chosen for the boat to have a velocity relative to the earth, relative to the bank, in other words, that's perpendicular to the riverbank. And then, although I don't say it here, how long would it take the boat in question 2 to get across to the other side?